Good afternoon, everyone. I'm very happy to be in India for the first time. I really took this chance to travel in India, fulfilling a dream. What I'm going to talk about is basically a very simple problem on a very simple setting. Essentially, we have just a 1D tight binding chain with a periodic boundary condition, and we have only one particle. So initially, the particle is in some eigenstate, some Bloch state, and then we can do two different things to the system. In the first case, we will periodically drive the system, drive the particle on some local site. In this case, if the driving is weak, we get kinks. In the second scenario, we do sudden quench. We change the potential of some site suddenly. And then in this case, we get sharp Cusps. In the second case, the Cusps will be a non-perturbative effect. The problem is very simple. The setting is very simple, but it has many generalizations, and there are many open problems. First, let us review, have a brief review of the 1D tight binding chain. We always take the periodic boundary condition. So it's actually a ring. This is the Hamiltonian. It's well known that the eigenstates are the Bloch states, basically plane waves on this lattice. This is the dispersion relation. The Q, the wave vector Q, is discrete. It's labeled by these integers up to an integral multiple of the lattice size n. So let us consider the first scenario. So this is the ring. Initially, the particle, we have only one particle. So initially, the particle is placed in some arbitrary Bloch state, say in this one. This is a stationary state. So nothing happens initially. Then from some time on, we turn on some harmonic driving. We take some arbitrary site, and then we start seeking the potential of this site harmonically. So under this harmonic driving, the particle will transit, will jump to all other Bloch states. The first quantity of interest is the survival probability, or the probability of finding the particle in the initial Bloch state. Numerically, the problem is very simple because it's a 1D problem, a single particle problem. So you can easily integrate the time-dependent Schrödinger equation. So here we have an example. The horizontal axis is the time, and the vertical axis is the survival probability. Here are the parameters of the system, and this is the size of the lattice. This is the driving period. This is the driving amplitude. For the Ki, we have the initial wave vector. So it's the 59th Bloch state. So the solid line is our numerical exact results. For this kind of problem, of course, you can do some analytics using the Fermi golden rule. So this is the dotted straight line is the Fermi golden rule prediction. Fermi's golden rule is a perturbative result, so generally quantitatively it's not good. So as you can see, the dotted line doesn't agree with the solid line, not well. The difference is visible. But here the point is not. For the solid line, it's a little bit strange. Initially, it looks like straight, and then there's a kink. It changes direction suddenly. And then after some while, again, it changes the direction. And here, there's a third change of direction. Okay, so now here we have we have decreased our driven amplitude. Initially it's 0.8. Now we decrease it to 0.3. So now we see, yeah, the Fermi's golden rule is very good now. And the dotted line, the dotted straight line is the Fermi's golden rule prediction. And here we have 3 different lines corresponding to 3 different initial Bloch states, 3 consecutive Bloch states, labeled with 60, 61, 62. So we say, initially the 3 lines overlap. They follow the Fermi golden rule prediction very well. Then at some moment, suddenly, they find out. And then, at the second moment, after the same period, the 3 lines changes direction simultaneously again. And after a while, they change direction again. So basically, the point is that if your driving is weak enough, you get these piecewise linear curves. The kinks appear periodically. Curve is piecewise linear. And the point, another point is that beyond this critical point, the evolution is very sensitive to your initial state. So you also have initial level dependence beyond this critical time. So we have tried to understand this phenomenon analytically. First, let us notice some essential features of this model. Here we have the spectrum, energy spectrum of the tidal band in Jiang. It's from -2 to +2. Overall, the spectrum is not uniform. The density of states is most dense as the energy bottom and energy the top of the band or the bottom of the band. As locally, especially in the middle of the spectrum, it's almost equally spaced. So you have, at least locally, you have the equally spacing, equally spaced spectrum. And another feature is that because your driving is only is on a single side, so the coupling between two arbitrary Bloch states, K1, K2, is a constant. It equals U over N. It's independent of your, it's regardless of the 2 Bloch states. So you always have the equal coupling property. Regardless of the distance, energy difference between these 2 Bloch states, the coupling is a constant. And the third point is that we have very sharp, kinks only when the driving amplitude U is small. So this means the kinks must be a perturbative effect. So, as it's just a perturbative effect, so we can do some standard textbook tight binding, time-dependent perturbation calculation. So this is the standard textbook results for the transition probability. So here we sum over the here initially your level is in your particle is in this Bloch state, and because of your driving is near resonance to some Bloch state up in the middle of the band. By the first order time-dependent perturbation calculation, we get this expression of the transition probability. Basically, we sum over all these energy levels. Yeah, we recognize the so-called sinc function square. The point is that this is verified by numerics. Only those near resonance states are significantly populated in the whole process. So we can somehow replace this realistic summation by some virtual summation. We replace the realistic energy spectrum, which is line uniform, by some uniform one. So imagine that you take these levels, near resonance, and then you extend it into a virtual spectrum, which extends from minus infinity to plus infinity, and are equally spaced. It's equally spaced as here. So now the summation problem is reduced to this summation problem. So now the m is an integer from minus infinity to infinity. So for the task now is to carry out this summation. So here we can introduce some scaled dimension this time, capital T, which is basically the level space in delta times the realistic time T. And when this dimension is time T, capital T, the transition probability has this expression. Here the W alpha function is basically a periodical sampling of this sinc function square. The sampling period is the dimension is time T, and for this periodical sampling, you also have a horizontal freedom. So that is characterized by the parameter alpha. The parameter alpha characterized is defined here. So basically, it characterizes the location of EF in the spectrum. If alpha is 0.5, then EF is located in the middle of two energy levels. If alpha is 0, then EF is in exact resonance with some Bloch state. So here, the problem is to calculate the W alpha function. For this kind of problem, we have the standard tool of the Poisson summation formula. So suppose you have to periodically sampling some function f. The problem, this summation problem can be converted into a Lala problem. So first you can do the Fourier transform of the function f to get the capital function, the capital F, and then the original summation problem is reduced to a periodically sampling problem of the function capital F. So you basically you convert from a problem in a real space to a problem in the momentum space. Now you hope that the transformed problem, the converted problem, is simpler than your original summation problem. In our case, this is indeed it is. So this is our original summation problem. Using the using the Poisson summation formula, we have to calculate the Fourier transform of the sinc function squared. But it's well known that the Fourier transform of the sinc function is just a window function. It's constant in this interval and vanishes outside. This is actually a result of the Pani-Venus theorem for the Fourier transform theory in the Fourier transformation theory. So once you know the Fourier transform of the sinc function, you can easily calculate the Fourier transform of its square. You just convolve F1 with itself. And then you get this triangle function. It's supported in this integral. It's supported in this interval and vanishes outside. So now, in this periodical sampling, the function sample has only a finite support. So here, the infinite summation problem reduce automatically to a finite summation problem. You have only finite number of non-zero terms here. So automatically, the summation is done. So in the end, you get your W function in this form. Here we have 4 parameters for the parameter alpha, 4 values for the parameter alpha. So you see that if alpha is 0.5, then it's linearly increased to some point, and then linearly decrease to 0, returns to 0, and then it's periodic. But the most important point is that if you reduce the time t is less than pi, then your W alpha function is just this linear function. Is independent of your parameter alpha. This is actually the Fermi's golden rule. There's no there's no alpha dependence. This is a very reasonable result. But beyond this point, then your W function depends on your alpha, on your parameter alpha, and depends on the depends on the interval the capital T belongs to. So it's a piecewise linear function. The slopes now depends on the parameter alpha, the integer m. So this basically this figure explains this figure. So So we have understood our numerical finding, understood the kinks. Personal kinks were observed long ago by people in quantum optics. These are two literatures pointed to us by our friends. So say 30 years ago, these people in studying this problem, they found these kinks, very sharp kinks. Basically, the problem is they have multi-mode optical cavity, and they put a twin-level atom in the cavity. And initially, your atom is in the excited state, and then the atom will decay into the cavity modes. So, in a single citation section, this model reduced to our ideal model. The point is that they didn't take the kinks very seriously. They didn't try to account for it very quantitatively. They just attribute it to interference. Yeah. The time. These are time. But actually, there is a very beautiful, exactly solvable model here. So here, suppose you have a continuum band extending from minus infinity to infinity and equally spaced. Besides this continuum, you have a discrete level here. And this discrete level covers to these continuum levels with a constant amplitude G. Initially, you put your system in this on this discrete level, and then it decays into the continuum band. This problem can be solved analytically very beautifully. This was done 40 years ago. I stay on the GBET. Here you see they're very sharp Cusps. Okay, so let's now come to the second scenario. In the first scenario, we choose an arbitrary site and drive the secant site periodically. Now, we just quench it suddenly. We just change the potential of this site to some value U, and then hold it fixed. So initially, your particle is going around the ring this way, and now you suddenly erect a barrier. So intuitively, it will be reflected from this Bloch state into its mirror image minus K, and then it will be reflected back. So here you have a Rabi oscillation picture. So the particle will oscillate between two groups of Bloch states harmonically. Numerically, this problem is simpler. Is even simpler than the former scenario, because now the Hamiltonian is time independent. So you just need to diagonalize your Hamiltonian once, and then the time evolution is trivial. So here we have the numerical results. This is time. This is the probability, the survival probability, and the reflection probability. These are the parameters. This is the size of lattice. This is your initial Bloch state. This is the amplitude. This is your potential, your defect potential. So you see, on a large scale, indeed, we have the Rabi oscillation picture. But there are some details. See, you you have very sharp cusps here, very sharp cusps here. They are equally spaced. And a very important point is that now it's a non-perturbative effect because you see the survival probability pi can drop all the way to 0. And then when it comes back close to 1, it shows very sharp cusps. And this process can repeat and repeat. It never deteriorates. Here we have some more examples corresponding to these parameters. This one is very regular. Pi drops from 1 to 0.5, showing a cusp dropping to 0. And when it returns to 0.5, showing a cusp, and then it returns to 1. And then this pattern repeats. It's a periodic function of time. And here the cusps are very, very sharp. So we also tried to understood the cusps here. Again, we have a very important numerical observation. So this is the dispersion curve. Initially, the particle is in this Bloch state. The numerical observation is that throughout the process, only those Bloch states in the vicinity of Qi and minus Qi are significantly populated. Those levels at the top or the bottom of the energy band have a negligible population. So again, we can linearize our model. We can replace this realistic model by a virtual model, which consists of two linear spectrum. One is a linearization of this branch, and the other is a linearization of this branch. Each consists of infinite number of levels, and the energies are equally spaced. So basically, the idea is very similar to what people do in the Lagrange liquid theory. To solve the dynamics of this ideal virtual model, first we can employ some symmetry. The model, the realistic model and the virtual model both have the parity symmetry. So it's invariant under reflection with respect to the defect site. So we can introduce some new bases with a definite parities. So we form these linear superpositions of the left-going and then the right-going states. And for the water parity states are already eigenstate of the virtual Hamiltonian or the realistic Hamiltonian because its wave function vanishes at the defect site. But the even parity states are not, and they are coupled by the defect potential to each other with some constant amplitude, which is independent of the energy difference between the two states. So we have infinite number of energy levels. They extend from minus infinity to infinity. They are equally spaced in energy, and they are coupled with a constant amplitude between any two levels. Your initial state is a right-going state, so you decompose it into an order parity state, parity state. This order parity states an eigenstate, so it doesn't evolve in time. But this order parity part will evolve in time. Formally, it's a superposition of all these even parity states. The quantity of most interest is psi naught, because the survival probability and the reflection probability can be expressed by psi naught. So here we have the Schrödinger equation for the psides. This part is because of the energy of the nth level. This part is because of the coupling. We note that this coupling part is independent of your energy index n. So we can introduce a collective quantity, which is a summation of all these psides. And then we can formally solve this first order ordinary differential equation. Formally, it has this expression. And then we can substitute this expression into the definition of our function S. In the end, we get this integral equation of the function S. Here we have a kernel like this. And for this kernel, again, we have a periodically sampling of some function. So again, we can use the Poisson summation formula and convert this summation to another summation. So it's it consists of delta functions. They are equally spaced in time. So here again, we have this the Heisenberg time, which is 2 pi over the energy level difference delta. So now your kernel is a series of delta functions. So this integral can be easily carried out. So in the end, we can solve the capital S function. It's a constant in the first period. And in turn, we can easily solve all these psi functions. Especially, we can solve the psi naught function, the psi naught amplitude. It's linear in time. It's a linear function of time. The point is that when t goes to approaches the Heisenberg time, psi naught approaches this value, which is of magnitude 1, but with a finite phase. So the point is that initially psi naught is 1, and all other psi's are 0. And after a while, psi naught returns to 1 except for a phase, and all other psi's returns to 0 again. So after that, the system just repeats this process. So here we have the picture of the evolution of the system. Initially, psi naught is located as 1 at this point. Then it travels linearly. It goes at a constant velocity on the complex plane along this line. And when it hits the unit circle, it's reflected elastically. And then it goes uniformly along this straight line. When it hits the uniform, when it hits the unit cycle is reflected again. And the whole process just repeats. So once we have the picture of this precise knot, we have picture for this probability Pi and PR. So indeed, because precise knot rotates on the complex plane. So overall, Pi and PR are also perform Rabi oscillation. And but now, instead of being piecewise linear, Pi and PR are piecewise quadratic. So here, each segment between the Cusps is actually a parabola. And when the Cusps show up, we have always Pi plus PR equal 1. This can be. This is verified by these numerics very well. So we have understood the second scenario too. So far, we have confined ourselves to the momentum space. We are always talking about Bloch state. But how about the the real space? What's the picture of what's happening in the real space? So we have followed the evolution of the density probability of the wave function at some site, some arbitrary site L. So here we have four different cases. So in each case, you see the density probability always jumps from plateaus to plateaus. So here you see you have very good plateaus, jumps from plateaus to plateaus. The picture is not when you erect the defect potential, you generate outgoing scattering waves. So here you see very well-shaped wavefront. Each time when the wavefront passes the site under observation, the density probability jumps from a plateau to another plateau. I don't think I have the time to go to the mathematics of the plateaus, so I just skip it. So this is a summary. We have studied a very simple single particle problem in a very simple setting. In the periodically driven case, we got a perturbative Kinks. And in doing so, we got a very simple, a very clear derivation of the Fermi's golden rule. And in the second case, we quench the system suddenly. And we get non-perturbative Cusps and plateaus. Both the Cusps and the plateaus are very robust. They last forever. They never deteriorate. The lesson is not simple models are not easy, especially when it comes to dynamics. Of course, the static property of our problem is very simple. We have very good picture of the eigenstate. So far, we don't have a good understanding of the dynamics. And the problem can have many generalizations. For example, here we have only a single, particle, which populates only a single Bloch state. You can also imagine that you have many particles and they are non-interacting and they fill a Fermi sea. And then you quench it suddenly or periodically driven at some point. In this case, we also have very interesting observations. So we don't have time to go to the details. Yeah, thank you.
Maybe I'll start with one. So if you go back one slide, could you spend a few more seconds explaining this, how to read this plot? So there are multiple lines that are they just staggered or?
Yes, they just staggered. They're equally spaced in time. Yeah, I just shift them upwards. Yeah.
So the lowest one is
the initial state. Yeah, a plane wave.
So you found these kinks as reminiscent of dynamical transitions. So I was wondering for the quench cases. So I was wondering whether you can also think of the kink appearing in a periodically driven system as the dynamical transition in the with a Floquet Hamiltonian. So then you map the problem in a quench problem effectively. And then if you do stroboscopic observations, and then perhaps this is just a dynamical transitions with Floquet Hamiltonians.
You mentioned the Floquet formalism. Yes, it's but frankly, I always think the problem is that we don't know how to do it analytically in the Floquet formalism. We can only do it in the Bloch state representation. As for dynamical transition, yes, it's a reminiscence of the dynamical phase transition observed by Hell in the transverse Ising model. But, so far, at least I don't understand the physics of the dynamical phase transition in the transverse Ising model. For me, it's pure mathematics. And for our case, we don't understand the physics. We don't have a physical intuition for this phenomenon. We only know the mathematics. We can get it quantitatively well, but we don't understand it.
Let's thank Jiang again for